So Dankrad Feist is our next speaker, and he's going to be talking about data availability checks and KZG commitments. And he is a researcher at the Ethereum Foundation working on Ethereum 2.0. And his interests are in cryptography, secure multi-party computation, and zero knowledge proofs. So take it away.
Yeah, hello, thanks for the introduction. So I'm going to talk about the data availability problem and KZG commitments. So here's a quick outline of my talk. I'll start talking about light clients and fraud proofs, because that's really the context that you need to understand this problem. Go into the data availability problem, talk about how Erasure codes solve the data availability problem, and then finally why we need KZG or KT commitments to polynomials in this process, and quickly go over how they work. Okay, so light clients. Light clients verify the consensus. So for example, proof of work, that would be checking that they are on the longest chain, but they do not verify the correctness of all transactions. So they basically only ask full nodes about the transactions that they care about. However, by using fraud proofs, we can protect them from incorrect transactions. So those would be fraud proof protected light clients. So to give an illustration how this works, so basically at the top you see the perspective of a full node. It has like a chain of block headers, and those point to basically a set of transactions, so the block bodies. But the light client at the bottom, they only follow the header chain, the chain of block headers, and then they will ask a full node for the information that they're interested in. So for example, here the light client is looking for transaction 3 in block 4, and then the full node replies, okay, here it is, and then they can include a Merkle proof in order to show that the information they have given is correct and compatible with the chain of headers. But now the problem is this: what if this block that is part of this header chain, this block body, contains an invalid transaction, right? So we added an invalid transaction to this block number 4. Now full nodes would actually not consider this to be the valid chain, because they verify, they're like, oh, this is not a valid block. That's not part of my fork choice. So they just exclude it completely. However, the light client doesn't do that. So in this situation, they would just be fooled, like the full node would give them this information and the light client would simply believe it. But we can introduce this additional mechanism that's called fraud proof. So we add this policeman who gives us gives the light client a proof that this chain that the full node has given the light client contains something invalid, this invalid transaction. And that fraud proof could be generated by anyone. So you don't need to trust some honest majority or something. You just need to be connected to a peer-to-peer network with some where this fraud proof can be distributed. And as long as you're not completely eclipsed, as long as you're connected to some honest nodes, then you should receive this fraud proof. So in this case, the light client would be protected, and they just say, no, thanks, I'm not going to follow this chain. I will, ask someone else, basically. Fraud proofs are basically this very short statement that contains a complete proof that something incorrect happens. So for example, transaction that's incorrect balances, so basically an incorrect state after the transaction. And the way they work is they contain the pre-state, the transaction itself, where the incorrect state transition happened, and a post-state, and they contain Merkle proof or witnesses, and that's basically a cryptographic proof that this transaction and the pre and the post state were part of the chain that is trying to be fraudulently presented here. However, there is one problem with this approach, and that is whoever that's whoever produced that fraud proof in the previous image could not have done so if the data to produce that fraud proof was simply not available. So in this picture now, we still have the same header chain that points to an invalid transaction. However, whoever produced that block simply didn't actually publish it. So they kept this transaction secret. Now this is still a problem because full nodes would not follow this. But now suddenly they can't prove it anymore. So the light client would still be following it because nobody can prove that there's a problem. They can see, oh, there's a header chain that doesn't come with its data. So there's something fishy, but you can't prove that data is not available. So they could at most send a message, hey, there's some data missing here, but then the light client wouldn't know who to trust. And this is a fundamental problem because data not being available is a so-called non-attributable fault. Because you cannot give a proof that data is not available. And what that means is that these two situations, so like I've drawn up two situations here. The first one is like a fraudulent block producer produces this block header with a missing transaction. They don't publish the data for it. And then like the good guy says, hey, so someone else says like this evil guy is trying to hide this transaction. And then they publish it afterwards, right? And so they claim it's been there all around, and whoever tried to raise the alarm just didn't see it, right? And situation B is different. Here the producer was actually honest. They did publish it. Then some other evil guy claims that they were trying to hide the data. And once again, afterwards, the good guy will say like it was always there. The problem is that the light client cannot observe which of these situations is the true situation. So whether the data was available from the start is not an objective fact. The only way you could check it is if you always check it all of the time, but even then there are problems, like there's all kinds of problems with network latency and so on. But we don't want that anyway. We don't want to check all the data because that's the point of being a light client, that you don't have to do that. And why? And yeah, this is such a big problem because one is like the light clients lose their protection from fraudulent transactions. But even if we know that data is always correct. So as an example, for ZK rollups, we always give a proof that all the data on the chain would always be correct. And in the case of ETH2 data shards, well, they only include data anyway. There's no validity condition. But even in those cases, it's still a problem because you could simply remove the data that now someone needs to access their account on chain. So you could, for example, add to someone's balance, which makes their witness invalid. So now technically they've got more money in their account, but they have completely lost any ability to access them. And that would mean these funds can never be used again. Okay, so how could we solve this? The naive solution is light client goes ahead and they just ask for some random samples, like give me some of these transactions, and if they're available, then I'll accept that probably the whole chain is available and you weren't trying to trick me. The problem is that the probability of catching, because it could be a single unavailable transaction, right? There could be one transaction that says print 1 trillion Bitcoin. Okay, so like, and catching that transaction, if you only do some random sampling, is too low. So that's why the naive solution doesn't work. So like, I'm going through a quick example here. So if you sample 10% of the data, then like the probability of catching the single fraudulent transaction is only 10%. And you see that like 10% is already a lot of data, right? We want light clients to be much, much lighter than that. And at the same time, 10% probability of catching it is too low. So we need some form of amplification so that this method becomes much more efficient. And the way we do that is by so-called erasure coding. So erasure coding works like this. You take the original data. So this is represented by the 4 blue blocks, D0 to D3. And you take a polynomial, oh, sorry, this should say degree 3 here instead of 5. So if you take a polynomial of degree 3, then any 4 points will always be enough to reconstruct the polynomial. Right? That's basic algebra. So if we take these 4 initial original data points, we put through those a polynomial of degree 3 and extend it with 4 more points. So we doubled the number of points, right? Then any 4 of these 8 points will be enough to reconstruct the polynomial. And this is called the Reed-Solomon code. It's just a fancy name for polynomial interpolation. And now if we do that, then sampling becomes efficient and much more powerful, because suddenly we don't need to ensure that all the data is available. We only need to ensure that at least 50% of it is available. And that means the number of samples we need to take suddenly becomes a small constant. It's not even dependent on the amount of data anymore. So if we query like 30 random samples and all of those are available, then the probability that more than 50% are not available, which is the requirement, because otherwise, like if more than 50% is available, then we can always reconstruct the data, right? So if you want to hide anything, you have to hide more than 50%. Now, if you only do those 30 random samples, then the probability is already 2 to the minus 30. So that's 1 in a billion. It becomes very hard to hide the data even by taking a small number of random samples. So with data availability sampling, basically the light client will at the start, while following the chain, always do this random sampling. For every block, they will say, give me like this number of samples. And then afterwards, they don't need to worry anymore. They basically know like the data was available. So like if there had been some kind of fraud, they would have been alerted by someone honest on the network. Right. Okay, so why is all this relevant? I was talking about light clients and full nodes and so on. Now, when we come to ETH2, then this becomes all even more important, because in ETH2, we have this architecture. We have the beacon chain, which has all kinds of administrative functions. And then we have the data shard chains where data is published. Yeah, those are basically the way we're going to scale Ethereum. Any validator, they always validate the beacon chain. Everyone always does that, but they can only be on one shard at a time. That's essentially the whole point of ETH2. Like, we want to scale it, and so if like everyone always has to validate everything, then there's no scaling, right? Then we would be still at the original problem. So we want this property that validators only have to check a single shard. But that means that they will become light clients on all the other shards, because they can't be fully validating. Like, they don't want to download all of them in the case of data shards. So they're actually light clients on all the other shards. So this means in the ETH2 design, actually pretty much everyone is a light client, except for maybe some people who are going to run super full nodes that validate everything. Right. Now there's one little problem or difficulty that we skipped earlier. So we have the data and the polynomial extension. But how do we know that the extension is valid? So like if someone could just like not do polynomial interpolation, they just make it up randomly, and then different different points would basically give different polynomials, so you can't reconstruct the data. So you could still hide data or like make different people see different data and so on. So that would still be pretty bad. And that's where we come to KZG or Kate commitments. KZG commitments are commitments to a polynomial f of x. So it's defined by this fi are the polynomial coefficients, and basically with KZG commitments you can compute a commitment C of f. See that's basically a short string of bytes. See it like a sort of a hash function, like that turns a polynomial into like this short string of bytes. And it has the special property that for any valuation, so we have some z in the domain of the polynomial, and y is the value at z. A prover can compute a proof pi of f and z, and using this commitment and the proof, a verifier can verify that f of z equals y. Right? They can verify that this evaluation was correct. But the crucial thing is they don't have access to the actual polynomial. They only have access to this commitment. So like the polynomial could be huge, like in this case, like we are talking about like hundreds of kilobytes, say for each 2 shard blocks. And but the actual commitment, the size of that is only 48 bytes if we use an elliptic curve like BLS 12381. And basically, this solves the problem of like what do we do if the block producer tries to commit to an invalid extension, because what we're going to do is we're going to give the polynomial commitment to f of x, to the actual polynomial, and then we just say that data block 0 is f of 0, data block 1 is f of 1, and so on. And the extensions are just further evaluations of the polynomial. So E0 is f of 4, E1 f of 5, and so on. And then like every time we take a sample, we'll get from the full node not just the sample itself, but we will also get a proof that this was the correct evaluation. So this is similar to like a Merkle proof, but in this case, that's why we also call them witnesses. In this case, the witness is this KZG proof, the proof that the evaluation of this polynomial was this particular value. And so this guarantees that all of these values are on the same polynomial. And a Merkle root, which you may be familiar with, like is a vector commitment. So it cannot guarantee this. It could also easily commit to 8 values. We can do that. But we would have no way of knowing that they are all on the same polynomial without opening them all, which is exactly what the light client doesn't want to do. Okay, so how do they work? This will be like, I'll go over it very, very quickly because I don't have much time. But yeah, if you're interested in it, then this is, you should see this more as a little teaser. My blog has like a description on how they work, which can be understood with relatively basic math knowledge. So we assume that we have a so-called trusted setup. So what does that mean? This S, that's a secret value, and nobody in the world should know this. So like we need some sort of MPC in order to create this, but let's assume that we have it. And basically what we have is S to the power of I, these monomials, and these brackets, they denote that we want them as an elliptic curve element. And the index 1 and 2, they are basically 2 different elliptic curves. We'll need 2 different ones because we'll need pairings, which I'll come to in a few minutes. And they usually only work efficiently over 2 different elliptic curves. And so one property, and the reason why I'm writing them in these brackets, is that basically elliptic curves give us this way of making computations over finite fields in a black box way. So you can't look inside these brackets. Means you can get this elliptic curve element, like for example s in brackets 1, and you can do computations with it, but you can't find out what s is, and you can't find out what s squared is, and so on. But you can make some computations with it. So what you can do is you can add 2 of them, and you can multiply them with a scalar, but you can't multiply 2 elliptic curve elements. Okay, so now we take a polynomial, and the KZT commitment to S is defined as the sum fi, and then we've replaced the variable, like the x to the power of I, by the trusted setup element Si in the elliptic curve. And now we use properties of the elliptic curve. So we can basically, we can do scalar multiplications. So basically we can pull the Fi inside the brackets because we multiplied the elliptic curve element by Fi. And then we can pull the whole sum inside the bracket. And so we see that actually the KZT commitment is S evaluated at S, but inside the elliptic curve, right? So that we can't actually compute. We can't compute f of s because we don't know what s is, but we can compute that value as an elliptic curve element.
5-minute warning.
Thanks. Now I'll have quickly go into pairings. So pairings are bilinear, is a bilinear operation. It's a function that takes elements from 2 elliptic curves, G1 and G2, and outputs them in a target group, GT. And the property of the pairing is that it's bilinear. So basically, if you take it's basically the same as what you know under bilinear and linear algebra, except the one strange thing is that the group GT, for historical reasons, we usually write it as in multiplicative. So this a times x, when you pull the a out, it goes into the exponent, and the same when you do it in the second factor. And below I actually made a mistake. That should not be a plus, but a multiplication. Yeah, but so it is basically a bilinear, and but the notation is often a bit messed up. And pairings. So I mentioned earlier that in the elliptic curve you can't do multiplication, as in you can't multiply 2 elliptic curve elements with each other. So for example, when you have this square brackets S element of an elliptic curve, from that alone, you can't compute S squared. Like that's impossible. But with a pairing, you can do that in some sense. You can do it in the target group, is what we say. So if you have the pairing of X and Y, then you can take the X out, give 1 Y and to the power of X, and then you can take the Y out, so you get X times Y in the exponent. So if we change our notations for target group elements, then we see that this basically means that the pairing of X and Y is X times Y in the target group. And so that means that you can actually, because we had these polynomial commitments, we defined them basically committing to f of x is f of s. And if we commit to another polynomial in the same way in G2, then we can compute the product of the 2 polynomials in the target group. And now we just need one more missing piece until we can see how KCG proofs work. and that's polynomial quotient. So if we take f of x to be a polynomial and y and z are field elements, then this quotient q of x, which is defined as f of x minus y divided by x minus z, is a polynomial if and only if f of z equals y. That's called the factor theorem. And so basically, I mean, it's easy to see, like the basic idea here is that if f of z equals y, then x equals z will be a zero of the numerator, so like it can be divided by x minus z. And if you reform this, then you see that this q of x times x minus z equals f of x minus y will have a solution q of x that is a polynomial and not a rational function, only if f of z equals y. And that is how that is what we use in order to create KZG proofs. So if you want to prove that f of z equals y, you compute this quotient, and if it is true, then that quotient would be a polynomial. And you compute the commitment to this quotient q of s, and then that's the proof. So that itself is the proof. And then using this pairing property, you can basically check this equation. So that's f of s minus y equals q of s times s minus z. If you look back at this equation, this is just the same equation, basically restated as an equation between polynomial commitments, and using the pairing to multiply them. And then yeah, you see that that this checks out exactly if f of z equals y.
We're out of time, so maybe finish your thought.
Yeah, that is it actually.
Okay, so I guess we don't have time for questions for this talk, but if you want to follow up over email or offline,